Hi, in this video we look at different strategies for finding the minimum or the maximum of a function when we are not necessarily optimizing on a closed interval. The problem is the following. Find the minimum of the continuous function f equals f of x on the open interval ab. Here a and b could be plus or minus infinity. The fact that the interval is open means that we cannot apply the closed interval method. This means that after finding the critical numbers in the interval, there will be further analysis of the function f and potentially its derivatives that will be necessary in order to conclude that one of the critical numbers is where there is a maximum or a minimum. Here are a few strategies that we can apply to show that there is a minimum at x equals c in the interval ab. We only consider finding the minimum to make this presentation shorter, but clearly all of the strategies presented here can be adapted to find a maximum. For the first method, we find a critical number c in the interval ab. Recall that a critical number c is a number where the derivative of f at x equals c is 0, so an x-coordinate where the tangent line is horizontal, or a number where there is a corner. The goal is to find a critical number c where the function decreases for x less than c and increases for x larger than c. This basically means that the function goes down and then up, and that c is where it reaches its lowest point. This is shown in the following figure, where the function decreases before c and increases after c, making c a place where there's a minimum. For the second method, we find a critical number c in the interval ab and show that the function is concave up. For this, we could show that f prime prime of x is larger than 0 for all x in the open interval ab. This is shown in the following figure, which shows a curve that is concave up and where at c the slope of the tangent line is 0. So this is where the minimum occurs. For the third method, we show that near a and b in the interval, the function goes to infinity. More precisely, we show that the limit of f as we approach a from the right and the limit as we approach b from the left are both equal to infinity. Note that if a is minus infinity, then in the previous limit, we would show instead that the limit as x goes to minus infinity of f of x is infinity. If b is infinity, then we would need to show that the limit as x goes to infinity of f of x is infinity. Now, since the function goes to infinity at both endpoints of the interval, there must be a minimum somewhere inside the interval. It would occur at some critical number, and therefore we must also find all critical numbers in the interval. Note that if we were to find a maximum, then this strategy would require us to show that the functions are at both endpoints of the interval goes to minus infinity. This is shown in the following figure where the function goes to infinity at both endpoints of the interval, here 0 and infinity. Here there are three critical numbers. In particular, at c1 there's a corner, and each of them is a candidate for a minimum. By evaluating the function at the three critical numbers, we would find that the minimum occurs at c1. Method 4 is to simply sketch a graph of the function f by studying the sign charts of f, f prime, and f prime prime, and the limits involved in finding all the asymptotes of f. This is a brute force method. It will always work, but may take quite some time. Note that for all of the previous strategies, we always need the critical numbers in the open interval. Therefore, to optimize, no matter what method we apply, we should first compute f prime, find its domain, in particular places where f is defined but f prime isn't, because those are values where there could be a corner, and finally solve the equation f prime of x equals 0. In the next video, we will apply all the previous strategies to a specific example to illustrate each of them. Thanks for watching.